Good evening. My name is Carter Pate, and I'm here to present on the topic of integrating wireless communications on autonomous underwater vehicles. I'll begin with a brief description of AUV development, followed by a thorough discussion of Gobi as a middleware, as that is the focus of my research. I will then show you some simulation results of Gobi in action and finish with a discussion of the next steps that we hope to take in the next semesters. So one of the first things that we learn about electric systems as children is that electricity and water don't mix. But these devices are a marked exception. Autonomous underwater vehicles, or AUVs, are a class of submersible, unmanned devices that are uniquely suited to underwater exploration. A given AUV, such as the EcoMapper shown here, has a number of antennae, sensors, and other electronic devices. But today, we are concerned with three in particular. The AUV front seat runs the EcoMapper's proprietary control software that translates heading and movement instructions into motor and fin controls. It does its job well, and we couldn't be happier with it. But in terms of research and development, it's a system best left alone. The autonomy of the autonomous underwater vehicle comes from a separate computer entirely. The AUV backseat runs Mission-Oriented Operating Suite Interval Programming, or MOOS IVP, to generate those heading and movement instructions, either from a predetermined mission or in response to its environment. It's this computer that allows us to generate missions for research and exploration. Now, autonomy is highly desirable in an AUV. In fact, it's the goal. But at some point, you're going to want to be able to communicate with or control your AUV. And absent a long, waterproof data cable, options for this communication are limited. Wi-Fi comes to mind as an easy answer. It's fast, it's reliable, and nigh ubiquitous in our modern communication infrastructure. But Wi-Fi, like all radio waves, is a form of light. If you've ever been out in the open ocean and looked down, you'll understand that light has a hard time propagating through water. For this reason, underwater systems rely on acoustics as their means to transmit data wirelessly. Our third component of interest, the Sub-Nero acoustic modem, is the device that facilitates that communication. By means of a UNetStack application, it sends and receives information as acoustic data. So we have these three devices, each running their own applications, and not all in the same language either. To that point, we need a translator. Enter Gobi. Gobi is an open-source C++ library for marine robotics projects. Secondarily, it's a simulation tool that supports faster-than-real-time multi-vehicle simulation. Primarily, it's a publish-subscribe middleware with convenient base classes for writing processes and drivers. Now, that's a lot of terminology, so let's stop and talk about what I mean. If the AUV's front seat is like the brainstem, then the AUV backseat is the brain, with the modem as its eyes and ears. Middleware is the connective tissue that ties these components together, passing and translating information as needed. As a middleware, Gobi is a publish-subscribe model, which means that a publishing application sends out data and the middleware distributes it to any application that's signed up to listen. Those are the subscribers. What makes Gobi special is its bring-your-own attitude. Its aforementioned base classes make it pretty easy to bring in your own transport scheme for data if you don't happen to like the defaults. Another thing that makes Gobi special is its nested communications interface. Now, a lot of things need to communicate to get an AUV moving. Vehicles talking to other vehicles, yes, but individual processes and even individual threads need to be able to communicate. The issue is things like latency and throughput can vary wildly between inter-process communication and inter-vehicle communication. Each layer requires its own scheme to handle and transport data, and Gobi provides a common interface between all of these layers. So what are these layers, and how does Gobi interact with them? Well, on the inter-thread layer, task to individual task, data is shared by means of a shared pointers system. That means as soon as data is published, every subscriber has instant direct access to that data. Keyword direct. The data isn't copied and sent to subscribers. Subscribers are given an address to find that data themselves. That means we don't have to worry about copying data because that takes time. And the message can be really as large as you want because strictly speaking, it doesn't go anywhere. That's why on the graph to the right, throughput is dominated by the inter-thread layer with trillions of bits per second. On the inter-process layer, the keyword is options. By default, messages are passed through Google Protocol buffers, or protobuf for short, but Gobi has support for 0MQ and DCCL right out the gate as well. But here's where that bring your own attitude really shines, because if those don't suit your needs, you can extend the inter-process application to any serializable data type. On the inter-vehicle layer, things get tricky, because this is the layer that we're not sending data across wires, we're sending it across large underwater distances. If you look to the right, inter-vehicle throughput ranges in the hundreds of bits per second, and we're operating at the speed of sound rather than the speed of electricity or light, which means we have a high latency system as well. So data transfer is slow, it's risky, and you can hardly transmit any data at once. In addition, the inter-vehicle layer on Gobi's side depends wildly on what specific modem you're using, because every model, every make, every modem requires its own driver to work properly. Gobi has a number of pre-made modules for modem drivers if yours is supported, but there's also a template to make your own if it isn't. Now I'd like to share with you some simulations done through Gobi's simulation software. Gobi is useful because it supports faster than real-time simulation, but what's really exciting is Gobi's ability to simulate multi-vehicle communication. I'll say that again, not multi-vehicle deployment, multi-vehicle communication. Here on the right, we can see a mission in which I've blown up the starting deployment to show a single unmanned surface vehicle, or USV, surrounded by 4 AUVs that are submerged. The USV is programmed to just follow the trail that's this outline of a fish, but the AUVs are programmed to follow the USV, giving it a wide berth to avoid collisions. This means the AUVs aren't running a pre-made mission. They are communicating in real time with the USV and responding in real time to avoid collisions and follow it. This is underwater acoustic multi-vehicle communication, and it's really exciting that we can simulate it. As a nice quality of life touch, Gobi interacts with a number of graphic interface applications for displaying these simulations. The one shown here on the right, P Marine Viewer, is technically cheating because in this simulation, movement and position data are always known in real time, which we can't expect from a in-the-field test. But Gobi's plugins with P Marine Viewer and Google Earth and OpenCPN display the data in a far less continuous manner that's more akin to what you'd see out in the field. So that's where I'm at with my research now, but before I go, I'd like to share with you some exciting milestones we hope to hit in the near future. A separate subset of my lab is working on a fully customized acoustic modem that is specialized to our needs. During and after that development, I will be in charge of writing a driver that's equally customized to that modem. This will be a change because with the EcoMapper research, Gobi has only been useful to us as a simulation tool. But in the very near future, we'll be expanding development to a new AUV entirely, the GaiaBot, which I'm shown holding here. Unlike our research with the EcoMapper, the GaiaBot will make full use of Gobi as a middleware. And perhaps most exciting, in the future, we hope to implement that multi-vehicle communication with multiple AUVs as a high-functioning robotic swarm. But that brings me to the end of my presentation. Are there any questions?
So you mentioned some real-time scenarios that might occur. Does Gobi, in the presence of potential latency issues, provide any kind of scheduling control or any way to help make sure that some real-time constraints are satisfied?
Yes, in the simulations, there's Some really sophisticated tools that are very helpful in this simulation. And yeah, there are means to simulate that kind of high latency environment to make sure you know what your AUVs are actually doing, because otherwise there'd be discrepancies between what they do in the field and what they do on paper.
What is the range of your acoustic communication?
It depends largely on the modem, but with our sub-Nero acoustic modem, it ranges from 4 to 5 kilometers, which I believe is 2.5 to 3 miles.
Speak any more to the low throughput of inter-vehicle communication?
I certainly could. So, inter-vehicle communication, it's tricky because we're moving through water and we're moving with acoustics, which is a lot slower, and we don't use it as often. It's not as developed as Wi-Fi communication. So where we can send whole messages that have a number of different data types, a whole slew of data, whenever we go to the inter-vehicle communication, we have to be very careful about the size of messages we're sending because throughput is so low.
Do you need to worry about the Doppler effect with acoustic transmission?
That's a good question. So for those unaware, the Doppler effect is this funny thing that objects do when they're emitting sound as they move. The sound kind of gets bunched up in the direction it's moving and fanned out away from where it's moving. It's why when a car passes by you on the highway, it goes meow. It's why that sound changes. So yeah, sound changes its frequency relative to you when the object producing it is moving, and that's absolutely a concern. But the good news is the math to correct it is surprisingly not that complicated and pretty easy to implement. So it's a pretty simple workaround.